All right, now, Ka and Kb, this is new stuff as of right now. When acid and base are conjugate pairs, the product of Ka and Kb should always equal Kw. So, you have a conjugate acid-base pair. Each one of them, because they're in the weak category, they're going to have a Ka and a Kb, and when you multiply them together, they should end up equaling that 1 times 10 to the minus 14. If I know the Ka of, say, acetic acid is 1.8 times 10 to the minus 5, I can figure out the Kb for acetate, because acetate would be the conjugate base in that particular situation. And all you would have to do is take the 1 times 10 to the minus 14 and divide it by that 1.8 times 10 to the minus 5. And as you would see, the acetate is not a very good base because it would be in like the 10 to the minus 10 category, so it would be a weak conjugate. And we're going to also be looking at the relative amounts of the conjugates to their other part of the pair. Usually one of the pair is stronger than the other. Let's take a look here. Examples of conjugate base pairs, acid-base pairs. So, if the base is ammonia, the acid is going to be a what? All I need to do to this to figure out the acid would be add an H plus actually, because then we would make it with a plus 1 there. We're adding an H plus in. So I've given the acid its hydrofluoric over here. How do I figure out its conjugate base? Take the H plus away, so we end up over here with F minus. Now I put a couple up here because I did tell you earlier that water's amphoteric and can act like an acid or base, but I also wanted to show you that there are others out there that are also amphoteric, can accept protons, and can also donate them, like HS minus, okay? So if this is considered to be the base this time, what would the acid look like? H2S. Good. However, if it was acting over here as the acid, what would the base look like? S with the 2 minus, right? So you're getting the idea of taking away and adding the H there. Now we have carbonic acid. So that one's going to look like what? HCO3 with minus 1. Okay, remember we're taking away 1 H, so we really add 1 negative to the charge there. And that would be hydrogen carbonate or bicarbonate, which is the stuff that's in baking soda, by the way. Sodium bicarbonate, that HCO3, that's what's in, everyday wonderful baking ingredient. Over here, the acid, in order to make carbonate, would be what? HCO3. So I just wanted to point out, too, in this particular list, as you see, like bicarbonate or hydrogen carbonate is amphoteric as well. So is the HS minus. Amphoteric species exist out there besides water, and you need to be able to add the proton or take the proton away. Okay? Just wanting to, so you write down a few of those examples. You don't have to write down all of them, but I did want you to write down a few of them. Okay? And keep in mind, too, that this particular base, any of the bases up here are going to have a Kb value. Any of these acids up here, because they're all in the category, will have a Ka value. So you can always do the Ka times the Kb to get Kw, and that's 1 times 10 to the minus 14. And they should always multiply that way. Now, exercise 1. Here, we're looking at comparing acetic acid and hydrocyanic acid. So C2H3O2 or HCN. Now do remember too that this could also, the organic way of writing acetic acid is at the top there. It's also known as ethanoic acid if you remember anything from your organic naming. But if you see that CH3COO deal, You know that's acetate, so pay attention to that it's acetate, and it can be written either way. We say this is the inorganic way to write acetate, this is more of like the organic way to write acetate. Okay, so you might see it back and forth written that way. Now it says calculate the Kb values for acetate and for cyanide, CN, minus. So all we would have to do here is do what? Kw equals the Ka times the Kb, right? So 1 times 10 to the minus 14, basically divided by our Ka, and that would give us our Kb here, right? And what does that value end up being? 5.6 times 10 to the negative 10? Yes? Let's do the other one. I'm just manipulating this equation, dividing it by Ka, you know, from the beginning. Doing that extra algebra step quickly. So its Kb is going to be 1.6 times 10 to the minus 5. So this is a simple calculation, but this also does provide us information about the strength here. Out of those two acids, which one is the stronger acid? Well, here are our two acids up here, the HCN and the acetic acid. By looking at their Ka values, I can tell which one's the stronger one, which one ionizes more. So which one ionizes more of those two? We're looking here at our Ka values. This one's 10 to the minus 5, which is a much larger number than 10 to the minus 10, correct? So the acetic acid is a much stronger, you know, or has the ability to create more hydronium in the water than the hydrocyanic acid is. But also the reverse is true, and this is where you need to pay attention. Looking at our two conjugates here, we have cyanide and we have acetate. Out of those, which is the more stronger conjugate base? This one is the stronger conjugate base. And that makes sense because if you have a weak acid, your conjugate base will be stronger. If you have a weak, a stronger acid, your conjugate base will be weaker. They multiply out to get that 1 times 10 to the minus 14. And if you look at those values and their size of their values, you can tell out of the pair which one's going to be the stronger one. So acetic acid is stronger than acetate, and the cyanide is stronger than the hydrocyanic in terms of the pairing. Okay? So if we're looking at comparing these two in a reaction, and we're looking at it from the acid perspective, the one that is going to be more dominant and controlling and ionizing would be the acetic acid. But if we were also looking at it in terms of their conjugates, the one that would be stronger and pushing it more towards the reactant side would be the cyanide. It's the stronger conjugate base here. So do pay attention to those Ka and those Kb values, their sizes, and you know, if one is the acid is stronger, that means the conjugate base of that acid is weaker. And if the conjugate is the stronger one, then the acid or base is going to be the weaker part of the pair. In terms of ionizing, of course. Anything about that? We're good? And everybody understanding how to interpret these values? I mean, the calculation is pretty simple, but looking at it for the conceptual understanding here, what those Ka and Kbs are telling us, how they work in the pairs. We're all good? Okay. All right, ways to describe acid strength. A couple of different ways that we can describe it. Ka value is large, it's a strong acid. If it's small, it's going to be weaker. And of course, this is just a generalized comparison. The position of the dissociation, if it's a large one, it's going to be to the right. That's why we put the arrow in just the one direction towards completion there. Okay? And if the Ka is small, we have the double arrow establishing an equilibrium position, but usually it's more to the left because there's less ionizing going on. Equilibrium concentration compared to its original. Basically, anything in the original that's initial, that's what that 0 means, initial value, they're going to pretty much equal each other because they break apart, dissociate, form hydronium. Here, the amount of the H being released to form hydronium is much smaller. Okay? And strength of the conjugate base, this one's much weaker, right? It works in a pair. So if you have a strong acid, the conjugate base is definitely weak. If you have a weak acid, then your conjugate should be stronger. But it is relative depending on looking at those Ka and Kb values. All right, concept check here. What is the equilibrium expression for this? How would we write this out? Just like before in regular equilibrium, you do what? Products over reactants raised to the power, although in most acid-base situations, most things are monoprotic, so they're going to not have powers, it's all going to be 1 mole. Now, there's an occasional situation where you might have a diprotic base or something, but for the most part, you're not going to see a whole lot of exponents in these. What is the one that we're going to leave out? Why? The liquid is a pure substance, concentration doesn't really change. So then we would do, Ka equals concentration of the hydronium times the concentration of the conjugate over the original concentration of the acid. So very simple. It's the same way you would do an equilibrium expression for equilibrium or KSP, following the same kind of conceptual way of writing that. The brackets, yes, we're still using brackets for concentration. Okay, this is all, focused around concentration because everything's, dissolved in a liquid. So you won't have to worry about any pressure things here because it's not going to be gases. But, so we'll be looking at the brackets and the concentration, yeah. If the equilibrium lies to the right, that means it would be on the product side. Therefore, K would have to be what? Large or strong acid. What do we compare K to normally? Q. We do compare it to Q if we have initials, but in general, when we're looking for equilibrium position. Greater than 1, less than 1, yeah. So here, it would be, it lies on the product side over here. Here's the reactants, but here's our equilibrium position over here on the product side. K is going to have to be what? Greater than 1. So the Ka would be greater than 1 here. Now if the equilibrium lies to the left, so we have reactants, I guess we should have double arrows since we're having equilibrium here. In this case, the equilibrium position would lie over here on the left-hand side towards the reactant. So if the K is going to be small, we know that, and therefore also the Ka would be what? Less than 1. So we're still going to compare equilibrium positions to the 1s. The only time you compare the Ks to the Qs is when you have initial concentrations and equilibrium concentrations, and you need to figure out which way it's going to proceed in order to establish equilibrium. So that's when we use the Q, is when we have initial concentration. Here we're just generalizing the conceptual basis of the equilibrium constant and the equilibrium position together. Because remember, the generalized idea of the equation, you can really start thinking about that way, is products over reactants. So if you have more products, more of the top number, your K should be greater than 1. If you have more of the bottom number, then your K should be less than 1. So you can think about it conceptually using that generalized equation as well. So once again, Ka would be larger than 1 and would be a large number. Ka would be smaller than 1 and be a small number. So looking at this particular generalized equilibrium equation, water is a better base than the A minus, which would be the conjugate base. Do the products or reactants dominate at equilibrium? Remember, what would make it a base? What's it going to do here? Accept the proton. So if it's accepting the proton, it's going to cause what to form? H3O. So if water's the better base, which direction is it going to proceed? Where is the equilibrium position going to lie? Should lie over on the product side, and it should proceed to the right. So if water's the better base, do the products dominate or the reactants dominate? The products would dominate. Very good. Yes, because we would be having this. This is more likely to occur if this is the better base, pushing it that way, than this one going this way. So this would be more like a tiny little arrow. So what's more likely to occur is the one that's acting as the better base is more likely going to push it to the other direction. So the products definitely will dominate if water's the better base here, and A minus is not as strong. It's not as strong a base. Okay. So does this mean that HA is a strong or a weak acid? Which way are we saying it's going to push over here? To the right. So the base, is accepting. So what about our HA? What's it going to do? It's going to need to donate, right? You can't have a base accepting an H without something donating the H. So in order for that to occur, we need to have our HA here on this side be the stronger acid, causing the water to accept the H, and the equilibrium position being over here, causing these to occur. So HA, in this case, if water is the better base and the equilibrium position we know is on the product side, that means HA must be a stronger acid. And we determined that based off of the previous question about the base, that the equilibrium position would have to lie on the product side and that they would dominate. Okay? So this is kind of working through the conceptual ideas of which way the equilibrium position would lie. Now, then, based off of we determined that the water's the better, is the better base, and so that it lies on the product side. Determined that HA must be the better acid, stronger acid. What is the value for the Ka? Is it greater than or less than 1? Products are dominating. No, over here we have the products dominating. So our K is definitely going to need to be greater than 1. Equilibrium has been pushed to the right here. Okay? Once again, just using that generalized conceptual products over reactants, if it lies on the product side, K has to be greater than 1. And since we're talking about acids, it's Ka. Let's look at a particular example where we have a couple things going on here. We have two sets of species, two conjugate acid-base pairs looking up at this reaction. We're going to discuss the value of K for the reaction. We have a Ka for our hydrocyanate right here, 10 to the minus 10. We have a Ka for our hydrofluoric, and it's 10 to the minus 4. So, looking at that, try to think about, we have an acid right here, right? This is our acid. So the F minus is going to be acting as the base, right? And over here on this side, that means the Cn minus is going to be the conjugate base, good, the conjugate base. And our HF is going to be the conjugate acid. Okay. Now, if we're looking here at our values, right, we have HF is 10 to the minus 4, and we have HCN is 10 to the minus 10. Out of those two, who's the stronger acid? Which one's going to be the stronger one? HF is definitely going to be the stronger one out of those two. Okay? So, basically, this one's going to be donating make the arrow bigger. Then this one, be much a smaller arrow, right? Not so big. So the HF donating to the CN is going to be a much more dominating process. It's Ka 10 to the minus 4. But what else do we know about the CN? Because if this is 10 to the minus 10 for the HCN, the CN is going to be what? Its KB is going to be like 10 to the minus 5 something, right? It's going to be a stronger KB, right? So, now we know which direction it's going to go. Which way is the equilibrium position going to lie? Over here on the left-hand side, right? So, the position is going to lie over here. So what does that tell us about our K value? Should be less than 1. Because it's going to, the equilibrium position for this particular reaction is going to lie over on the left-hand side. Any questions on that? Looking at that particular kind of example there. Comparing Ka, Kb values, looking at conjugate acid-base pair strength, equilibrium position, anything you want to hear again. Lots of process, lots of detail here. Now, it's something we can always come back and revisit later. You know, some of these things takes a moment to, you gotta let it sit with you for a little bit and go back and review it in order to really, truly grasp the concepts. All right, now, we're gonna calculate the actual K for this overall reaction. Now, this is kind of like what we did before. I don't know why my arrows are out of place. SmartBoard did not like to put them up there where they're supposed to be, I suppose. All right. So we have to look at this and approach this similar to what we did with Hess's law and the other equilibrium manipulations where you had series of steps going on here. Okay? So what we're going to do here is we're going to separate them into their KAs. And then we're going to manipulate them and calculate. Now we're gonna break these up into their series, because each Ka is representing that acid reacting with water to form its conjugate base and hydronium. So we'll separate them both into their two-step series first. So let's go ahead and do that. So the first one, HCN plus water. This is giving us our first Ka value, right? And that's going to give us hydronium and cyanide. So that's the first one in the series going on here. And this is the Ka is the 6.2 times 10 to the minus 10. Right? Now what's the other thing happening here? We have our HF is the other acid. It should be reacting also with water. If it has a Ka value, it's really reacting with water, establishing equilibrium here. Okay, forming hydronium and its conjugate, and that gives us its Ka value of 7.2 times 10 to the minus 4. Now, what do we need to do in order to make it look like our overall reaction up here? We need to do what to the bottom one? Anyone? Flip the bottom one. So we're going to flip this bottom one. What happens to our Ka then? 1 over reciprocal, right? Just like before, we're going to do the reciprocal. Okay? So we flip this one, we get F plus, and then we get H2O plus HF. Right? The hydronium, these blue hydroniums cancel, the waters cancel, and do we end up with our overall reaction? Do we have all the right people in the right places? Yes, 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 right? Everything's in the right side now. So now what do you do with your Ka values once you've manipulated, or K values once you've manipulated them in their series? It's just product now. Multiply. So we would do our 6.2 times 10 to the minus 10 times 1 over the 7.2 times 10 to the minus 4. And we calculate that. And the overall Ka for this particular reaction, which involved 2 weak acids with their, conjugates, we get 8.6 times 10 to the minus 7. These series step type problems keep coming at us in a new little tweaked version. So it's the same kind of concept as before in equilibrium. We're just now applying it to the acid-base equilibrium. Oh, this is fun. Let's get started. pH of 0.5 m molar aqueous solution of the weak acid hydrochloric. Let's think about this. Well, what did we do in the past when we were given information? What do we need to think of first? Step 1 is to look at our concentration, look at our Ka, and also consider what? What's the other thing we need to consider before we move on in our problem? We need to decide, because there are 2 possible reactions always occurring in the acid-base equilibrium. You have the actual acid itself, the HF. You also have the self-ionization of water that you need to consider. So if we're looking here, what's the self-ionization of water again? Self-ionization of water, we have this reaction where we would get hydronium or hydroxide. That's the Kw value is 1 times 10 to the minus 14, right? We already said this one is 7.2 times 10 to the minus 4 is its Ka value, correct? So always in your back of your mind, make sure you consider that self-ionization of water. We have 0.5 molar. We have a much larger Ka out of the HF. We have a pretty decent amount of concentration. So which one of these is going to control the pH? The HF one. Remember in the previous set of notes, we talked about the one where it was like the hydrochloric was at 10 to the minus 11, where it was a very minute amount of concentration. In that case, that particular example, the self-ionization of water would have dominated the pH, and it would have been right around 7. But we do have to consider this every time in the back of our heads, because they like to put an occasional question on there where they give you this very weak concentration, and you're supposed to realize, oh yeah, it's not going to do a whole lot. The self-ionization of water is the dominant species, and therefore the pH is going to be right around 7. So always have that in the back of your head to figure that out. So we're going to have HF control it, though, because its Ka value is much larger, and there's a pretty good concentration, 0.5 molar. It's not a tiny amount of concentration like a 10 to the minus 11 would be in terms of molarity. Okay, so we're looking at, discuss the K values. So now we have to set up a rice chart. I know you guys are all excited to do some more rice charts. I know you guys want to relive the rice chart from last year, last unit. So this is a modified rice chart like the KSP ones, because what do we have here as one of our reactants? We have liquid water. So what do we do to this section? We get to cross that one out. We don't have to put it in there. But we are going to do lots of rice. And you'll see with acid-base equilibrium, though, they are a little bit different than regular equilibrium, because 1, everything's dissolved in solution, and 2, it becomes very formulaic. So it becomes the same kind of system that you would do, the same kind of change. It's 1-to-1 molar relationship. So these will pretty much start following the same pattern. You'll see that pattern over and over again. So our initial concentration of our HF was 0.5. Our initial concentration of hydronium and the fluoride are going to be around 0. This is as it's reacting with water. And we still do our change based off of that molar relationship. So what are we going to do for the HF? Subtract X. And what are we going to do for the hydronium and for the fluoride? We're going to add X. So there you go. Based off of the molar relationship, remember, you're going to lose whatever out of here on HF will be gained over here on this side. That will be gained by the hydronium and the fluoride. And since everything is 1-to-1, whatever you gain in hydronium, you also gain in F minus. So those all should be equal. We would put in our values. Any ideas what to do next? Yes, what's that thing called? That K thing?
Expression.
K expression. Yes, we're going to use our K expression. Very good. Ka expression. So our Ka expression here is going to be what? Well, what's our expression first? H3O plus on top, concentration of the F minus over concentration of the HF. And like I said, this is going to become very formulaic. So you might, once you get really good, you might be able to start skipping the race chart part of it, okay, and just go straight to this. Because you'll know, oh, I'm going to subtract this, I'm going to add this. Also, there's another nice little added tidbit that you get to do here. Because our Ka is 10 to the minus 4, right? The Ka was 7.2 times 10 to the minus 4. Now, 10 to the minus 4 usually will be okay for the 5% rule. Just like in KSP, these X values are very small amounts, right? Okay, like in KSP, remember how they were so small we got to eliminate them?
Yeah.
Well, in this case, it should be small enough here to also be able to eliminate it. We call it the 5% rule in acids and bases. If it's less than 5% that's ionized, then you get to eliminate the X, and you don't have to do the graphing part of trying to solve and find the intersection, or using the quadratic formula. Nobody wants to use the quadratic formula. That's no fun. So here, we will solve it, and we will look for eliminating that X. So when I put it in here, and you can do it both ways. You can graph it, and you can solve it this way as well, and tell me that and see if there's any difference, because there shouldn't be any difference. So in this case, we do 7.2 times 10 to the minus 4 equals X times X, right, over 0.50 minus X. But because this is a large number, and we know this X is going to be a small number, we get to eliminate it. So really then, all you have to do is multiply that up and square root it to get your overall X value. So what would the X value be then, once you calculate it? I'm getting 0.019 molar. So if we were to do our subtraction, okay, this would be a very small amount here. And the X value right here is going to be the concentration for both of the hydronium and the F minus, but we're looking for the what here? What's the overall goal? pH. We need the pH. So if we know our hydronium concentration, what do we do to that to figure out our pH? Negative log. So you negative log that, and you'll get your pH value. Right? Negative log that, and you get your pH value, which should be 1.72. Why would I put 2 digits over here to the right again? Remember, this one does not count in terms of significant figures. Remember, the .019 is two significant figures. The two to the right of the decimal are counting for your significant figures for pH. Well, the pH, HF is not driving the pH. HF is hydrofluoric and it's still together. The only thing that could make the pH is the hydronium. This is the H+. Remember, H+ attaches to water to create the hydronium. That's the acid driving ion that drives the pH. Well, that's how much we're starting. But basically, we're saying, if you look here, when you put 0.5 molar HF in water, only 0.019 is actually going to ionize into the hydronium and actually going to break apart. Most of it stays together. Most of it stays together. Only a tiny bit of it really actually turns into the ions. And actually we're going to look at now how much of that it would actually turn into the ions. So if we had 0.019 molar turn into ions, how much did we start with? 0.05 times 100. What is the percent that actually ionize? It's going to be a very small amount. So it's only 3.8% actually turned into ions, actually became the acid part. And since this value, this 3.8, is less than 5%, we do get to do that elimination. And that brings us to the 5% rule. When X, you can eliminate X and ignore it if it's less than 5% of the original concentration. That's when you're allowed to do that. You're allowed to eliminate the X. And all of the problems that I've looked at and seen and worked, I kind of have a couple different scenarios that I look at to decide whether or not I'm allowed to eliminate the X. The first thing I look at is the Ka value. Okay? So if your Ka value, okay, is less than, or equal to the 10 to the minus 4 or something, you usually get to eliminate X. Eliminate X. Okay? It's when it's around the 10 to the minus 3. This time you usually have to graph it. Okay? You're not going to be allowed to eliminate the X. You can always go back in and check it like I just did. I did the 0.019 over the 0.5 and check the percentage. Was 3.8 less than 5%? Yeah, so I was allowed to eliminate it there. You can always go in and quickly check your percentage to make sure it's right. If you go in and you check your percentage and it's over 5, go back and graph it and get the intersection. Do you see what I'm saying? If it ends up being 7%, oh, well, I can't eliminate X, now I got to go back in and graph it. Okay? But usually you can tell by the Ka values. If the Ka is 10 to the minus 4, 10 to the minus 4, sometimes I check those just in case, but if it's above, like 10 to the minus 5 or above, so anything definitely less than 10 to the minus 5, eliminate. You can definitely do that. Here, you might want to check it, do the quick little equation if it's 10 to the minus 4. 10 to the minus 3s usually do not come out right, and you do have to graph it. So I will tell you, I've kind of looked at that, and I've noticed that pattern as I've worked these problems. 10 to the minus 3s, the concentration usually and the percent ionized is usually higher than 5%. Okay? So you get to eliminate, look at your Ka value. If it's like 10 to the minus 10, that's a really small Ka. You definitely get to eliminate that. Yes? You can, but it won't affect the overall equilibrium concentration of the original amount. Because that change in X will be so small. Yeah. You can still graph it every single time if you really want to. It's an extra added step. If you don't need to waste that time, eliminate the X, do the quick calculation, move on. Yeah. Definitely looking for ways to make our time go faster, right? Percent dissociation or ionization. It's a formula. I know you love formulas. Formulas, amount dissociated over the initial concentration, or the amount ionized, you could call it amount ionized, times 100. So percent ionization, this is another way you might see it, or the amount ionized. Basically forming that H plus or that OH depending on which one you're doing, but will determine your percent dissociation or percent ionization. Now, this is the trickiest part of it, and I put it in big bold letters up here. For a given weak acid, the percent dissociation increases as the acid becomes more dilute. I'm going to show you why. I don't know if we'll get to it today, but we'll show you why that happens. Most people would think, well, if you're adding more water, you're making it weaker. It should go down. It shouldn't be as concentrated. Well, it isn't as concentrated. We're not really talking about how concentrated it is. We're actually talking about the percent that gets ionized. So we've got to make sure that we get this concept down. Make sure that you write that down. It's very important that the percent ionization actually increases when you dilute. That means adding more water to it, making the concentration weaker. Yes, you're doing that, but the percent dissociation actually increases. And it's a Le Chatelier principle. We're going to show you why that happens, but keep that in mind. Most people get confused by that. That's definitely something to memorize and understand. Question? Well, yes, you're adding more. When you dilute, you add more water. Where is water in the reaction? It's on the reactant side. You add more reactant. Which way does it push? To the right, making more ions. So the amount that gets ionized goes up. Although the concentration actually becomes weaker. Do you see how that can be confusing? So, yeah, let's keep that in mind. And we're going to go back over that. Like I said, there's an example that shows that particularly happening. The solution is 8 molar formic acid, this HCHO2 compound. You're going to see some really random organic acids, by the way, too, throughout the rest of the AP chemistry. They throw in some very interesting acids. Anywhere where you can take off an H, though, can be an acid. So formic acid is 0.47 ionized in water. Then you want to calculate the Ka for the formic acid. So, any idea of where we should begin? Reaction, good. And since we're doing Ka, what are we reacting it with? Water, right? HCHO2. And what are we going to get over here? We'll take off that H. This becomes a what? Minus. And then we end up with our hydronium. Good. Because that H transferred over. This H went over here, remember? Okay. What else are we going to need to do? What is our initial value of our formic acid? 8. What is our initial value of our formate? That's what that's called. And our hydronium? 0. Good. So what would the change be normally? Minus X, plus X, plus X. And you'll see that these ones become pretty standard formulaic rice charts. They don't, and you might get to a point towards the end where the rice chart, you don't even have to do it anymore because you see it's pretty formulaic. So this ends up being minus X, this ends up being X, and X. Well, are we going to be able to figure out our X value? Yes, we can figure out our X value. How can we figure out our X value? Okay, so basically 0.47% of 8 molar is going to be our X value. That's the amount ionized. These are our ions here, guys, right here. Yes, you could use the percent ionization equation, which is basically just percent here, which is all we really need to do is take 0.49% of 8. And how do you do that? Alright, so yes, you could divide this by 100, you know, and then what? Multiply it? And what does our x value get to be? This is just using percents here. 0.0376 m, right? Okay. So far, so good? Basically, in here, this would be 0.0376. This is going to be 0.3076, 0.0376. We figured out what our x value is. Now, if I wanted to find Ka, what do I need to do? Do the equilibrium expression. Yeah, let's do that. Okay, so Ka is going to be 0.0376 times 0.0376, right? Over 8 minus 0.0376. If you're not seeing where I'm getting my Ka expression, remember it's going to be the concentration of the formate times the concentration of the hydronium over the concentration of the formic acid. That's where I got it from, if you didn't see that, or you weren't thinking what I was doing. I basically substituted in my value here, in my value here, for these two, and then this was substituted in down below. And what does our Ka end up being? 1.8 times 10 to the minus 4. And yes, technically, if we're looking at our digits up here, this one has 2, this one has 3. We should keep 2 at the end. Calculate the pH of the 8.00. Use the data from the previous slide. How can I do this very quickly? Correct. Remember, it's the negative log of that hydronium, right, is going to give us our pH. So we know that value. We just found it, right? So we can easily find the pH here. And what's our pH going to be? 1 point, and I guess technically we should go with 2 sig figs. So we can only go out 2 decimal places because we are still sticking with the idea of the 0.47% driving the sig figs. Don't forget the 2 decimal places past the one there representing the significant figures. And our pH, I actually rounded it to the 2 digits, the 3.8 here, since really we were dealing with the 2 digits from the percent ionized amount of 0.47. So end up, and remember the negative log of hydrogen is really the same thing as the negative log of hydronium, because they really are pretty much the same entity there. The H attaches itself to water to make the hydronium, which is the acid factor.